Nacional Pedro Enriquez Ureña, UNFU University. And for us, it's a great pleasure that you, Dennis, accepted our invitation to our university to present this talk, and that will be named Deep Learning for Software Engineering. And Dennis, I apologize for the pronunciation for your last name, Denny Poshyvanyk.
Yeah, Dennis Poshyvanyk, that's correct. Yep.
Great. Is sharing his time from William and Mary University, and he has great experience with this talk. And this is a talk that he has already made, and he is participating through the ACM, one of the most important organizations for um, machine learning in the United States, and in Dominican Republic we have a chapter that is joined by some members that are in contact and connected to the university from Adoprosoft, Mr. Ariel Gonzalez and Mr. Luis Concepcion. So we are very grateful to have you here. And we have students from different careers. Some of them are IT engineers, some of them are still studying, and some of them are professors. So the stage is yours. Thank you very much, Dennis.
Okay, so thank you so much, Hector, for introduction, for inviting me. I'm excited to be here, and of course, on this slide you see it's April 13, it's May 13, so I'm stuck a little bit in the past, but you will see why, because today I actually wanted to talk about the past, a little bit present and future of deep learning for software engineering. So I'll talk about some projects that we've done in the past, and I'll talk about what is going on right now, and I'll also tell you where the future is likely to be heading. But before I start, let me just very quickly mention ACM. As Hector said, I am currently ACM speaker, and ACM is an association for computing machinery, and it's a premier global community of computing professionals with more than 100,000 people across 170 countries. And the mission of ACM is to help computing professionals to do their best. And again, I'm proud to be a member of ACM. And thanks to this program, I'm presenting today. So let's jump straight into the talk. So it's no longer a big surprise. Everybody, and when I say everybody, everybody is using tools like GitHub Copilot or Claude Code or whatever your favorite tool is for writing code, or ChatGPT. But when I started doing this research more than 20 years ago, nobody was doing this and nobody was thinking about this. So this was literally my dream, to have an AI coding assistant at your fingerprints, doing code completion, code reviews, program repair, or things like that, right? And 20 years later, my dream finally came true. We have plenty of these tools, and these tools are really, really, really good. I mean, they are helping us write code. They're helping us to do code review. They're helping us to hunt bugs, and do all sorts of wonderful things. And indeed, well, the goal of software engineering over decades was always automation, right? If you read software engineering papers in the past, you probably noticed that most of software engineering papers have to deal with automation. So we would like to automate various software engineering activities using machine learning or artificial intelligence. And again, we see a lot more automation since 2022, when ChatGPT literally blew up the world, or took the world by the storm. But before that, automation was a long-standing goal of software engineering research, and literally hundreds and hundreds of papers in before pre-LLM era have been working exactly on this, trying to automate daily activities that programmers do, and it has been a very prolific area of research. So how do we do automation, or how did we do automation in the past before advent of deep learning? Well, we obviously used machine learning, we used information retrieval, but with machine learning, canonical machine learning techniques, we actually had to come up with heuristics or handcrafted rules, right? And we had to rely on human expertise. So we had to do a lot of this manual work, right? To find features, find these handcrafted rules. So we would spend paper by papers on discovering and handcrafting these rules, training machine learning algorithms like support vector machines, etc. And at the same time, as we all know, traditional machine learning techniques or canonical machine learning techniques have some limitations because we have to manually derive features, and all these features are subject to human error, as well as our inability to fully exhaust feature space. Kernels are complex, which can be difficult to map and identify, but also it's hard to extract pertinent and important features from data sets. And finally, most importantly, the representations of these machine learning techniques are fairly shallow, right? They were really flattened vectors, and we had to map these complex features of data into these shallow based representations. So this is our traditional machine learning techniques. And when I say traditional classical machine learning techniques, I spent many years working in this area of using machine learning to automate software engineering tasks, and I call this age before LLMs as a golden age of machine learning for software engineering research, because most of the effort we would put into crafting those features and training the model, which is obviously not the case these days. However, something big happened several years ago. First of all, we had all these open source repositories, GitHub, GitLab, so forth and so on, which contain massive amounts of data. Also, we had massive advances in modern architectures. And all this, obviously, a combination of these two factors led to this big thing which we're observing these days, where all this data was fed into deep learning algorithms, and suddenly these algorithms starting producing useful insights or salient patterns now that developers can use to their advantage. If we compare canonical machine learning on left-hand side and deep learning on right-hand side, we see that most of the parts of the algorithms are the same with respect to this part that in deep learning we have these rich hierarchical feature embedding. Like in neural networks, we have multiple layers that are able to encode or embed all this information using multiple layers. Whereas in canonical machine learning techniques, they're based on flattened vector-based representations. And again, deep learning can effectively be used to extract features automatically. So we no longer manually extract these features, but we can extract them not only from natural language, which is related to software engineering artifacts like source code, comments, bug reports, but also derivative software engineering artifacts such as call graphs, execution traces, or even graphical data like graphical user interfaces. And if we look into the past 10 years or so, we see that deep learning for software engineering has been covering a number of software engineering tasks, ranging from code comprehension, code generation, traceability, summarization. So no stone has been unturned. Deep learning has been taking over literally the whole world of software engineering. And various architectures have been applied. We started with RNN, encoders, decoders, CNNs, and now obviously transformers are dominating the world. So deep learning literally is tackling every single stage of software development, starting from requirements, design, implementation, testing, maintenance. It's everywhere. Okay. And in particular, I would like to show you some of the research that we've done in our research lab over the years. And again, we focused on various problems like automating model application design, code completion. We actually wrote the very first paper on using neural based approaches for code completion. At the time, people were using simple language models, and we actually wrote the very first paper on using neural code models for code completion, clone detection, code reviews, program repair, test assert generation, mutant generation, bug reporting, traceability, link recovery. So all these are examples of tasks that we've been working on over the years. And today in my talk, I will briefly look into the past, and I'll show you the history of some of the projects which are very, very deep to my heart because they were among the very first project in the space that sort of started this whole area of deep learning for software engineering. And these two projects are related to maintenance and design phases of software engineering. So first, I'm going to start with the task of mobile application design. And again, there are literally hundreds of thousands of applications out there. You go to Google Store, you go to App Store, and we have hundreds of thousands of applications covering all aspects of our lives, right? And one important aspect of successful applications is not just functionality that they provide, but also high quality graphical user interfaces that are important. They are as important as the underlying functionality. However, if you look into the industrial workflow, how these graphical user interfaces actually created, and I'm not talking about some weather app or calculator app developed or vibe coded by standalone developers. I'm talking about industry grade applications which are created by companies. They usually follow the following cycle where we have a separate UI UX team and where we have a separate development team. And usually this process goes like the following. UI UX team usually creates a mock-up of the application. They send it to development team, and then development team works on this, and then they produce a mock-up of this application, and then this mock-up goes to UI UX team, and then designers actually find some issues in that mockup because they say, well, look, your prototype is good, but it's not actually matching the design because the design that designers usually send to developers are crafted in Photoshop, so it's just literally a bunch of pixels, right? And designer and developers actually sending them a mock-up of the or they sending them actually prototype of the application with clickable buttons, and they say, well, this button is misaligned, or there is a different type of UI component, or we should be doing a custom component here, so forth and so on. So this feedback between UI UX team and development team goes on, and it may take multiple cycles before this is all resolved. And the core of this difficulty is the need to bridge a broad abstraction gap that literally necessitates reasoning about accurate user interface code from either pixel-based graphical representations of GUIs or digital design sketches. And typically, this abstraction gap is bridged by developers' domain knowledge. So developers know, oh, I know this is a button. Oh, I know this is this type of Android component, or this is that type of Android component. And developers, when they look at this mockup, they are capable of recognizing discrete objects in a mockup that should be instantiated as components on the screen, and they can easily categorize them into proper categories based on the intended functionalities, and they can rearrange them based on this hierarchical structure. So again, this process may go on and on until finally it's done. So in fact, in one of our studies, industrial studies, we find that during this process, there are lots of design violations that are usually created by developers as they actually design this application from the smoke. Resource violation, text violations, layout violations, and you can go and read our ICSI 2018 paper for more details. But what I wanted to say, at the time when we wrote this paper, this was a very, very active research area. And the idea that we had was, what if we try to bypass this iterative process of going between UI, UX team, development team, and back and forth and back and forth? What if we try to take this mock-up drawn by designers and try to automatically produce a prototype of the application that contains all these components? So this was obviously an ambitious goal, and there was some existing work at the time, but none of these papers at the time were able to do what we wanted to do. So the field was basically wide open. So in order to design a solution to do that, we tried to answer the following question. So one question was, how does a developer translate a GUI mockup into code? So first, obviously, they detect or identify GUI components that exist in that mockup. Second, they classify these GUI components into their constituent types. And finally, they assemble the GUI components into hierarchy and they stipulate styles. So that's what developers do in practice. So in order to do that, we essentially wanted to design the system to automate all these three steps being detection, classification, and assembly. And we ended up building a fairly sophisticated solution that contains data mining, dynamic analysis, computer vision, obviously deep learning. At the time we used convolutional neural nets, and also some techniques from data mining and computer vision for actual application generation. So you can see here a fairly complicated solution, which I'll explain to you step by step. And essentially, I'm going to ground my explanation into these three phases. So the first phase is GUI component detection. So one way to detect components which are given to us in the mockup is using computer vision, right? And some work has been done in the past, which we tapped into. We can use algorithms like Kenny's edge algorithms, wedge dilation algorithms, counter bounding boxes algorithms. And the goal behind using computer vision is to take that mockup and then produce a whole bunch of boxes, as you can see them on the right-hand side, telling us that there is some sort of component is in the box. We don't know what component, but computer vision tells us that this is a component that we need to recognize. Okay, so this is phase one. And phase one can be slightly more easier if we actually get mockups, like for example for Android applications that are created in Market, which is a plugin for Sketch, and we can export some of these mockups as combination of XML and JavaScript. So if that is the case, if it's not just a bunch of pixels, then parsing these components becomes much easier. Okay, and in this case, we can fairly precisely tell you that these are locations of these components on the screen. The second phase, this is where things get interesting because this is where deep learning resides. At the time, convolutional networks revolutionized the task of image classification. At the time, CNNs were approaching human levels of classification accuracy, and this is what we decided to use in our solution. So just to give you very brief explanation what CNN is and how it works, imagine that we have an input which is an image. It's decomposed into an array of matrices or a tensor, where each matrix represents the intensity of one of the color channels of the image, or RGB channel. So then this filter kernel to the first convolutional layer is applied to the tensor, where it slides across the matrix and performs convolution operations to transform the input matrix into a new matrix that represents abstract image features. And then this process is repeated through the different layers of the network, and between each layer, a set of weights that represent the importance of features extracted at each layer. So at each layer, we extract weights that represent the importance of this feature. And after single pass through the network, we see that in our case, it gives us an incorrect classification, right? So basically it tells us text view, but in fact it's image button. So it made incorrect classification. So in order for us to train this network, what we can do, we can calculate the error gradient and we can back propagate it through the network, and we can adjust the weights between layers so that they become more accurate. So next time we have a data point similar to this, hopefully it gets classified into image button and not text view. Okay, and obviously we're gonna do this hundreds of thousands of times for hundreds of thousands of images so that the network can learn to properly classify images of components. Okay? But it's kind of easy, right? If you have training data. But in our case, $1 million question is that how can we extract a large enough data set of training images, right? Because we want to be able to classify all these components on the screen correctly and say this is a button, this is some other component. How can we obtain a lot of training data like that? So this is where mining software repositories and automated dynamic analysis comes into play. We actually had to build this engine that automatically mined thousands of applications from GitHub, Google Play, and we actually built an execution engine that automatically executes every single application that we mined, and it would use a systematic GUI exploration that automatically navigates a target application's graphical user interface in a depth-first search manner. So basically, on the first screen that it gets, it would exercise all tappable, non-tappable, typable components, all components capable of accepting text inputs. And then during the systematic exploration, we used GUI Automator, and this is, by the way, the tool that comes with Android SDK by default. That would, at any moment in time, at any transition during the systematic exploration, it would generate an XML file, and it would tell us that's exactly what you see on the screen. These are exactly components and the types and locations. So essentially, by doing the systematic exploration for every single application at any moment in time, we could take a screenshot of that state of the application, and we could extract all the metadata using the UI Automator that comes with that screen. And that's how we create this massive training data set to be able to train convolutional neural network to do this classification. And again, this was massive undertaking, just extracting this data. We actually need to do a lot of engineering. We actually had to build this parallelizable solution of virtual and physical devices so that we can run all these mined applications and extract all this metadata. So, and finally, once this network has been trained, the final step, after we recognize all the types of the components using CNN that you see on the screen. So again, remember that the first step, given the mockup, we're just going to draw bounding boxes. And we're going to say, we have some sort of components there. We don't know what they are, but we know they are components. In the second step, convolutional neural network will tell us that's a type. Given this bounding box and the content of that bounding box, that's a button or that's something else. Okay? And once we have that information in the third step, we are we're actually constructing GUI hierarchy by doing by using KNN, and in this case, basically what we do, we mine a whole bunch of GUI hierarchies from these applications, and then the input to our algorithm is essentially a set of classified leaf node components that you see on the left-hand side from CNN, and the output is a GUI hierarchy. And to do that, we essentially use a corpus of all the mined clean screens and GUI hierarchies that we mined from thousands of applications. And then this GUI hierarchy generated by KNN, essentially what KNN does, it tries to match all these leaf nodes to existing hierarchies that we mine from Android applications. So we try not to reinvent the wheel. We're trying to pull pieces of these GUI hierarchies from existing applications, and then we stitch them together and again, this process may be done multiple times for multiple data points from our data set. And once all leaf nodes are matched, apologies here, I need to go through this again, I tapped back. But during this process, the goal is to produce the final GUI hierarchy for our mockup with all the classified components. And finally, we have GUI code generation and color quantization step to produce a fully functional prototype of the application. So I know I'm running a little bit. I have only half an hour left, but I want to cover much more. So I'm going to very briefly talk about how we evaluated this. Obviously, we took thousands of applications, we mined thousands of screens, and we labeled hundreds of thousands of GUI component images, and we compared our CNN-based classifier to bags of visual words. This is uh, um, support vector machine-based technique. And that's the data that we used to train our classifier for different types of GUI components that you see in the rows. You can see a number of training, validation, and test samples. So if you look just into the results, this is, by the way, our confusion matrix for bags of visual words baseline. So this is our canonical or shallow machine learning based technique. The overall accuracy, if you use just support vector machines, is 65%. And obviously, this accuracy is not good enough for our test because that essentially means if I give you a mockup and there are 10 elements on that screen, only 6 of them will be classified correctly. This is low accuracy because now we're going to take that as an input to GUI hierarchy matching. And with such low accuracy, we're going to end up producing mockups which are way off from our original mockup. So that's the result for our CNN-based technique. And as you can see, CNN results are really, really good. I mean, they're much, much better than support vector machines, were around 91%. And what we did, we actually digged into the results to understand where it makes mistakes and why. And the good news was that the confusion matrix illustrates that most of these misclassifications are typically skewed towards similar classes. So, for example, image buttons are primarily misclassified as image views, and edit tags are misclassified as text views. And such misclassifications in the GUI hierarchy would be trivial for experienced Android developers to quickly fix. Okay? And also we did the visual similarities, we compared a whole bunch of metrics, we did statistical tests, and finally we also did usability studies with developers from Google, Huawei, and Facebook or Meta now. And we got very good results. We got very good feedback. Developers from industry were telling us this tool was really useful and we want to do this. And just to give you a feeling what kind of prototypes our approach can generate, you can see an original mockup on the left-hand side. So this is literally a screenshot. And the actual functioning prototype of the application is on the right-hand side. So this is example for TextGram, this is Zillow, this is Bank of America, Giphy, Netflix. And again, if you want to know more about this paper, look it up in Transactions on Software Engineering. This work was done by Kevin Moran as the first author. He's my former PhD student who is currently an assistant professor at the University of Central Florida. He's still doing research in the space to this date. So if you're interested in the latest and greatest in GUI-based deep learning applications, look up Kevin's work. So the second piece of work that I wanted to tell you about, which we've done in the past, is related to code reviews. And we as software developers know that source code evolves whether you want it or not, right? And developers have to do maintenance tasks all the time. And the way they do maintenance tasks, they take source code and they apply some sort of transformations to fix bugs. For example, in this case, we may do corrective operations which would be aimed at fixing discovered problems or bugs. In this case, a null check is added before invoking the method on the variable myList. Developers also do adaptive changes, like instead to perform to basically keep software product usable. In this case, developers change the signature and behavior of this method to return a Boolean value. This is an example of adaptive change. Perfective operations are intended to improve performance or maintainability of code. So in this case, understandability of the code has been improved by adding JavaDoc to the method. And finally, preventive changes aim to detect and correct latent faults in the software product before they become effective faults. In this example, developers decided to initialize the list in case it's null. And again, what we notice is that we have a lot of data in open source repositories, millions or billions of changes which have been done in these millions of repositories. And what we can see every single time as a recurring theme is that developers do these code transformations across all the projects. So the goal of our research was to automatically learn from code features, change patterns, that then we can automatically apply to do our tasks. Okay, and essentially we wanted to train these deep learning based approaches to take the code before and change it to the code after. For example, to repair a fault or to fix a code change based on the code review. And at the time, we tapped into neural machine translation. And neural machine translation is an end-to-end deep learning approach for automated translation. And at the time, it significantly outperformed phrase-based systems without the need of creating crafted rules. And again, we've seen lots of very famous and powerful examples of using neural machine translation. So at the very high level, neural machine translation models are comprised of an encoder and decoder, and both are recurrent neural networks. And again, these are RNN-based architectures that we used at the time. Right now, these architectures are obviously transform-based. And an attention mechanism in these RNN-based systems helps aligning the input tokens to the output tokens in order to facilitate the translation. So the encoder essentially reads the input sentence and then generates a sequence of hidden states. And those hidden states are then used by decoder to generate a sequence of output words representing the translation of the input sequence. And here, the attention mechanism is represented in this image by the lines of different thickness that connect the hidden states of the encoder to the states of the decoder. Okay? So in order to do this, we didn't want to train these neural machine translation approaches just on random changes. We wanted to train them on meaningful code changes. So let me explain what I mean by meaningful code changes. So almost every meaningful software project out there is developed and managed using version control system. And it has at least a master branch. And when developers need to perform some changes to the code, rather than committing directly to the master branch, the best practice usually is to first create a new branch and then perform all those changes in that branch. And then once you're done with those changes, a pull request is performed, which is usually followed by a code review process where other developers on the team examine the changes and leave comments, which could lead to more changes and adjustments. And finally, if the code review passes and the pull request is accepted, the code review is merged with a branch. So this is what we refer to as a complete and meaningful code change, which has been reviewed and accepted. And such process with branch and code review is now obviously a de facto standard at pretty much all software engineering companies. Okay? So the question that we asked at the time is, can we actually automate this entire process? And the answer is yes, to a certain degree. And we came up with the following approach where we mine code changes, extracted transformational pairs, then we abstracted the code, and then used we trained neural machine translation approaches, and then we evaluated them. And again, we just dealt with meaningful code changes, not commits. In order to do that, we also build a crawler for Garrett, and Garrett is a code review system, and we extracted the data from Android on overt repositories, and overall we extracted data from 339 repositories, and we extracted data not just for random commits, but for all pull requests which have been reviewed, accepted, and merged. So these are high quality changes, not just random changes, not just bulk changes, but high quality changes. And that's essentially what you see here. So basically, we take a file before, and then we are taking the actual change which have been reviewed, approved, and merged. Okay. So in order to do the diff, we actually use a tool which is known as Gumtree diff to perform method mappings between before and after versions of the same file. So Gumtree diff is able to perform the mapping using semantic anchors, which actually works even in the presence of many changes. And then for each pair of methods, we perform abstract syntax tree based differencing, and we extract the list of AST operations performed. So for example, in this case, an if block was added in this method. And next, we consider only the method pairs for which we detect an AST operation, and then we discard all the remaining ones. So we refer to these methods as transformational pairs that formerly are represented by the method before and the method after, and the list of AST operations A. So we will use these transformation pairs as an example to learn how to translate the original method into a changed method. Okay? So there are some reasons why we decided to go only for method granularity at the time. At the time, methods usually implemented single task of functionality, they provided enough context, and finally, files or classes may be too large to learn patterns or transformations. Again, remember this work was done in 2019, before transformers, before the scale of models that we're dealing with today, so we had to deal with those limitations. And at the time, we also had vocabulary problem because English dictionary contained 171,000 words, and developers are not constrained by any vocabularies. Just computing number of unique identifiers in our dataset, we ended up having 370,000 unique words. And this was a problem for neural machine translation approaches at the time. So to address this limitation, we came up with a process which was called code abstraction, which allowed us to keep all the Java keywords, separators, and essentially we wanted to come up with generic representation of code, something like this, using this example. So we take this method, then we abstract this code by assigning IDs, and we have some lookup table where we put those IDs, and then we feed this abstracted code to trained neural machine translation approaches. Again, generates abstracted change code, and then to go from abstract changed code to concrete code, we do the process which is called concretization, where we map back all the IDs with the real values to generate actual changed code. Again, we trained our encoder decoder based models. We again performed fairly extensive experiments by varying all sorts of parameters. We also wanted to be able to generate multiple solutions, so we used beam search to track multiple hypotheses at the same time. And for the sake of time, I'm not going to go into quantitative results, but I'm going to highlight some of the qualitative results. And this was really, really interesting because in my experience as a researcher, I find much more fun digging into the data and understanding the data than just automatically computing some numbers and reporting tables and doing statistical tests. So what we wanted to do in this qualitative analysis, we wanted to understand types of changes that the model was able to learn and types of transformations that model was able to learn to apply automatically. And we essentially built a taxonomy of all the changes that we manually analyzed, and we classified them into three types: bug fixes, refactorings, and other types of changes. And when it comes to bug fixes, you see all these types of bugs that the models were able to learn and generate, all these types of refactorings that the model was able to generate, and other types of changes. Again, that types that include changes to method signatures, adding, deleting, replacing code, as well as types. So this is one particular example of refactoring where an anonymous class was replaced with a lambda expression, and the model was able to perform this change automatically. And the good news is that this change matched perfectly to what the Vert developers did during their transition to Java 8 code. So this was a real change which was performed by real developers, and the model was able to learn this. And keep in mind that this was done in a non-contaminated fashion. So when we checked against this result, this was not in the training data. So this was really, really cool. This is another example of refactoring where the model merges to catch blocks into one. And besides this, obviously, we applied neural machine translation for other tasks. We used it for program repair. We used it for generating mutants. This is a particularly cool one because here, instead of training models on going from buggy code to fixed code, like for program repair, we went the other way around. We actually we actually trained the model to introduce bugs into the code, which is obviously the whole purpose of mutation testing. We also used neural machine translation for third generation, and again, all these papers were cornerstone papers in our field across all these different areas. Of course, when transformers showed up on the scene, we immediately studied the applicability of transformers like T5 models for exactly the same tasks. We applied them also in code review context. This was one of the early works where we used code and comments to actually produce comments and automatically do code reviews, or just take code and produce comments. So this was as far as our previous work is concerned. What I wanted to tell you is that in 2019, actually was one of the co-organizers of the NSF workshop on deep learning and software engineering, and literally 7 years ago, we tasked the committee and attendees of that workshop to understand where we're heading across two dimensions. One is deep learning software engineering, how we can leverage deep learning in order to automate and improve existing software engineering tasks, and also software engineering for deep learning, where deep learning techniques are viewed as a new form of software development that needs tool and process. And I co-organized it with Bashaki Ray, and our steering committee was a number of highly influential researchers from industry and academia. And some of the future research directions that we identified at the time, and I'm happy to say that all of them panned out to be very important future directions, as we can attest now. One of them is combining features learned with deep learning with empirical software engineering knowledge, so that we see a lot of work happening these days. Leveraging and combining heterogeneous sources of software engineering data, this is something that we've been doing quite a bit. Developing architectures tailored for software engineering data, systematic reproducible research methodology, ethical and social considerations, development of tailored clean community data sets, so forth and so on. And let me just highlight a couple of these. In software engineering, you can find wealth of papers, empirical papers, empirical studies that have done obviously deep investigations into certain research phenomena. And one question that remained is how we can take some of that deep empirical knowledge and incorporate it into these deep learning based models to help us explain these models, right? So, for example, this work, and this work is from physics, leverages deep learning to discover representations of Koopman eigenvalues from data. And this work obviously benefits from the power of deep learning while retaining the physical interpretability of Koopman embeddings. So a work like this, in my opinion, is still very, very much needed. Like, for example, in software engineering domain, code-specific byte pair encoding, or BPE algorithm that would take into account underlying properties of source code based on filtering vocabulary, based on how we do word splitting or subword splitting. And again, this was one of the areas that picked up since then. Interpretability, in my opinion, is a really, really, really important area because everybody is using deep learning. Everybody is using neural large language models these days, but to this degree, to this day, they remain black boxes. And this is one of my very active research areas. And again, what models do, they keep exploding in size, right? And understanding efficacy of these language models obviously is a very, very difficult task. Like one of the first papers that I tried to understand performance of Copilot on GitHub contributions, discovered that early models of ChatGPT or Copilot were generating lots of security vulnerabilities. Not surprisingly, because they were learning on security, on code containing security vulnerabilities, so that they kept generating security vulnerabilities. And at the time, and still, there is still growing skepticism that the broader NLP research community had regarding the utility of current automated metrics for natural language understanding and generational tasks. So because they tend to overestimate model performance and provide only shallow comparative insights into actual model performance. So in our work, we've been trying to sketch a better path forward for having actionable interpretability pipelines to help us actually understand why large language models make decisions that they make. One of the projects that we've been working on was trying to explain code generated by large language models in terms of the underlying abstract syntax trees or underlying code features that the model was using to make the decision. So, and to this degree, we also use causal inference to help us understand which particular code features actually help to contributing to that particular explanation. So one example here I have is local explanation with AST-based concepts. Let's say we have this piece of code that we're trying to autocomplete. Let's say our original prompt was just the name of the method that we were writing. Our technique would actually map all these identifiers and their probabilities from the softmax layer into this abstract syntax tree, and this visualization would actually tell us that these identifiers were responsible for this particular prediction. Okay, so that would give a developer a pretty good view that would tell the developer that's what is responsible for prediction that we are making here. But even more importantly, there are all these cases like this, like for a given prompt in one, you see a piece of code that was generated for this prompt that contains a security vulnerability. In this case, it's a data leakage. It's actually very important to answer the question something like which tokens T in the prompt influence the generation of vulnerable code Y. And this is where we use causal inference or causal local interpretability to answer that question, to go back to the tokens or concept that contributed to that data leakage. And again, this is work in progress. You can see some of the most recent papers related to interpretability on my website. And if you have any questions, I would be more than happy to follow up with you over email on those papers that I did not have time to present today. So what is future work on now on software engineering for deep learning? Because for now we talked about deep learning for software engineering, but the other way around, building systems, software systems that contain deep learning components. What do we need to do as software engineers? So let me actually quote here Andrei Karpathy, who used to be a director of AI at Tesla. And Andrei said it very eloquently. He said, neural networks are not just another classifier, they represent the beginning of a fundamental shift in how we write software, and they are software 2.0. So in software 1.0, and that's what we've been doing for decades since invention of programming, we literally were writing programs, we're taking data, we fed them into machines that produce some output. But now with neural networks, we are giving them a lot of training data, and then these neural networks are producing the program, right? So, if I ask you to manually write a program to recognize different types of birds, you would look at me like I were insane, right? Because to write a program by hand to do this complex task is very, very, very difficult. This task is even difficult if you use canonical shallow-based machine learning techniques. But if I ask you to do this by hand without using any machine learning, that would be an incredibly difficult task. Whereas if you have a whole bunch of image pairs and actual answers, let's say you had million of examples of birds and labels for these birds, all you can do is to feed them into some famous architecture, train it on these set of images and labels, and essentially what you will do or you will get as an output, you will get the program because you will get a trained neural network, which is essentially a program, right? Because it could accept as an input an image and it would produce a label as a classification result. And the idea here is that we can now discover programs by literally by gradient descent, right? So we give a rough sketch, a skeleton of the code, which is now case neural net architecture, and then it will identify a subset of program space to search and use computational resources at our disposal to search the space for a program that actually works really well, right? We're going to search for a program that classifies these two kinds of birds really, really well. And in the specific case of neural networks, we restrict the search to continuous subset of the program space where the search process can be made. Okay? But at the same time, what has been discovered early on by giants like Google is that these deep learning based systems or software 2.0 or systems that contain deep learning components in them are buggy. They contain a lot of technical debt. Okay, and especially some of the earlier versions of the systems contain a lot of glue code. So in one of the first case studies by Google, they found that 95% of code in those software 2.0 systems is glue code. Okay, and obviously these are developers of yesterday and these are developers of these days. But what is interesting is the traditional software development lifecycle that you see on the screen is actually changing completely in the case of software 2.0, because now we need to worry about things like defining problems, defining goals, collecting data, preparing data, training models, integrating models, managing these models. And there are all these challenges that now we have in the era of software 2.0, like development challenges, maintenance challenges, verification and validation challenges, debugging challenges, deployment challenges, security, privacy, explainability. So all these are big challenges that we are facing today. So when it comes to maintenance challenges, let's drill down into some examples of those. We have technical debt, technical data dependencies. So machine learning, deep learning systems code and data level, they contain technical debt. So infrastructure code infers significant technical debt. Mature deep learning based system may contain 95% glue code connecting various machine learning libraries and packages. There is very little or no support for evaluating data dependencies for deep learning based systems as compared to many existing tools for existing classic software where static analysis can be used. Deep learning based systems frequently reuse pre trained parameters from other datasets or transfer learning, which adds dependencies to the data and other evolving models configurations. Machine learning, deep learning systems, they also follow back practices like experimental paths or dead flags in traditional software. Configuration management and evolving hardware is also a problem. So again, there is a lot of work that needs to be done, but I believe we are living at this highly unprecedented, exciting times where software engineering research comes together with machine learning and deep learning research to tackle many of these challenges. So again, I'd like to thank sponsors, National Science Foundation, Cisco, who funded this research. I would like to thank all of my current and former students who've been working in this area. Many of these students now professors or industry leaders working in companies like Microsoft, Google, so forth and so on. One of my students, for example, Michele, he's leading a team of researchers at Google right now to actually develop the next generation of development tools, which are based on deep learning and LLMs. And he told me that I have to be doing research in agent-oriented workflows, or if I don't, we'll be left behind very, very quickly as software engineering researchers. So That's pretty much all I wanted to share with you today. So thank you so much for your attention. And now I would be happy to accept any of the questions that you might have.
Thank you very much, Derek, for that magnificent talk. So let's open the space. If anyone is so vivid and so interested in having any questions, and Dennis is more than happy to answer them. So you can use the tool of the lifting your hand, or you can send a question through the chat. And so let's see if there's any question. Either they are sleeping or it was too clear. Okay. There are a bunch of applauses on the reactions. So most people are indicating that they enjoyed the talk.
Thank you.
So let's give a time of 1 minute to see if there's someone um, with any question. Otherwise, we can conclude the session.
Okay, sounds good.
Okay.
And again, if you have any questions, I would be happy to answer them over email.
Very good. Very good. Well, if there's any Spanish speaker, gonna switch just for to 1 minute. Si alguien tiene alguna pregunta sobre la conversación de Dennis, le pueden enviar también consultas por correo y él se las va a estar respondiendo lo más pronto que pueda. Así que muchísimas gracias chicos por conectarse. Si no tienen ninguna pregunta en vivo o a través del chat, eh, esta fue una sesión cortesía del Congreso CIPS en 2026 y también del capítulo de ACM de Santo Domingo, así como con el apoyo dado por SASO. Muchísimas gracias. Thank you very much, everyone, for your attendance, and have a great rest of the day.
Thank you. Have a good day, teacher.